Hi, welcome to the video on torque slip characteristics covering motor, generating and braking regions of three-phase induction motor. So to begin with, as the induction motor As the induction motor is located from no load to full load, so its speed decreases and hence slip increases. Due to the increase in load, the motor has to produce more torque to satisfy the load demand. So the torque ultimately depends on slip, as explained in the previous video, the slips and significance. The behavior of motor can be easily judged by sketching a curve depends on the slip, which will be explained in the next slides. The behavior of motor can be easily judged by sketching a curve obtaining by plotting torque producing against slip of induction motor. So the curve obtained by plotting torque against slip at S is equal to 1 and S is equal to 0. As we know, the operating slip of an induction motor is between 0 to 1. So it is called torque slip characteristics of the induction motor. It is very interesting to study the nature of torque slip characteristics here. So as we know, the torque is proportional to, from the above equations, it is proportional to S into R2 divided by R2 plus SX2 whole square. To judge from the torque equation, we can see that for any constant voltage, supply voltage, E2 is also constant. So we can write the torque equations as T proportional to S R2 by R2 square plus S X2 square. So now to get the nature of the torque slip characteristics, let us divide the slip range from 0 to 1 into two parts. So 0 to 1 only I am dividing into two parts, that is one low slip region and high slip region. So for low slip region, it is observed that S is very small. Due to this, the term S into R2 is also, S into X2 is also small comparatively to R2, so that it can be neglected. So SX2 can be neglected. So you get only the S into R2 divided by R2 square. So which is proportional to S. So if R2 is constant. So when you come to the high slip region, so before that, hence in low slip region, torque is directly proportional to slip. So if you observe, this is the x-axis and this is the torque y-axis. So since torque is directly proportional to S under low slip, so torque increases as the slip increases from 0 towards 1. In the high slip region, so that is hence the graph is straight line as you see here, that would be a stable region. As you observed, OA is the stable region. So hence the graph is a straight line where at n is equal to ns, s is equal to 0 and t is equal to 0, no torque is generated because n is equal to ns. Motor stops if it tries to achieve the synchronous speed. So torque increases linearly in this region, that is between 0 to a. So for high slip region, slip is high. So as I said, slip is approaching close to 1, from 0 to 1. It can be assumed that the term R2 is very, very small comparatively to SX2. Therefore, R2 gets eliminated in the denominator and the only left variable would be S into R2 by SX2 whole square in the denominator, which is proportional to 1 by S. So torque is inversely proportional to slip. That means torque should decrease as the slip is increasing. So this is the unstable region of the slip torque characteristics. So in high slip region, it is inversely proportional to slip. So it is like a rectangular hyperbola if you look at this curve. So when load increases, load demand increases, but speed decreases. If you look at the slip decreases, speed decreases, because slip is in this direction and speed in the reverse direction. So in high slip, torque is proportional to 1 by space, so torque decreases as slip increases. But torque must increase to satisfy the load demand. So as torque decreases due to extra loading effect, further speed is also decreasing and slip further increases. So again, torque decreases with the for the increase in the extra load. So therefore this region is called unstable region. So for straight line we call stable region of operation, and rectangular hyperbola in this the dotted line gives the unstable region of operation. Now it is an obvious question for all of us that up to which value slip torque characteristics represent stable operation. So in low slip, as I said, between 0 to S is equal to Sm. So it attains the maximum torque here. The maximum torque the motor can produce as load increases is Tm. So which is this point. So which is occurs at S is equal to Sm. So the linear characteristics of the torque and slip would be up to maximum slip, that is S is equal to S. Beyond this, if the load is increasing, the motor slip acts dominantly, it increases, and whereas it takes a shape of the rectangular characteristics here, hyperbola or rectangular hyperbola. The motor always so ranges S is equal to 0 and S is equal to Sm, that is a low slip region, which is a stable operating region, and motor operates from Sm to 1, which is high slip region, and it is a rectangular hyperbola. So the motor can continue to rotate at any point in this region. So at S is equal to 1, N is equal to 0. That means the motor produces a torque called starting torque, denoted as TST at this. So the entire torque slip characteristics are shown in this figure. So now coming to this torque slip characteristics covering motoring, generating and braking region. See, observe this. We have three region. That is one braking region, one is the motoring region, and one is the generating region. So if you observe the motoring region, the slip is always between 0 to slip is 0 to 1. Okay. If it is less than 0, okay, if it is less than 0, so this is slip is 0 and it is 1. So if it is less than 0, it enters into the generating action, and if the slip is greater than 1, it enters into the braking region. So always the three phase induction motor operates in this region, that is the slip varying from 0 to 1. So let us see how this characteristics has been explained. So when the slip is in the region 0 to 1, this is the region I'm talking, 0, 0 starts here and this is the 1, slip here. So the machine runs as a motor, which is the normal operation of an induction motor. So the rotation of the motor is in the direction of the rotating field, which is developed by stator currents. So in this region, it takes electrical power from the supply lines and supplies mechanical power output. So the rotor speed and corresponding torque are in the same direction. So when the slip is greater than 1, the machine works in the braking mode. So this motor is rotated opposite to that of the rotating field. So in practice, two of the stator terminals are interchanged. We change the phase sequence, which in turn reverses the direction of rotating magnetic field in this region. So the motor comes to quick under stop because it is producing counter torque, which produces a braking action. So this method by which motor comes to rest is known as plugging. Only care we need to take is that the stator must be disconnected from the supply to avoid the rotor to rotate in other direction. To run the induction machine as a generator, now this is the region where slip should be less than 0, that is slip should be negative. The negative slip indicates that the rotor is running at a speed above the synchronous speed. Now how to bring the induction motor to run above the synchronous speed? So we need to give an external externally we need to make the induction motor to run above the synchronous speed. So we use a uh, prime mover basically. So we use a prime mover to bring up the speed of this induction motor, which is above the synchronous speed, so that it works as a generator, synchronous generator. So when running as a generator, it takes a mechanical energy and supplies electrical energy from the stator. Thus the negative slip in this generating action takes place, and nature of torque slip is reversing, which is exactly the reverse of this induction motor, because it is generating. So this shows the complete torque slip characteristic, showing motoring, then generating and the braking regions. So the torque ratios are normally calculated, that is with respect to maximum torque and the full load torque. So speed torque characteristics, when you look at this, We have seen torque slip characteristics of an induction motor. To compare the performance of induction motor with DC shunt and series motor, it is possible to plot speed torque curve of an induction motor. So at n is equal to ts. So if you look at n is equal to ts, the motor stops as it cannot produce any torque. It is at 0. So the induction motor cannot rotate at synchronous motor. So at n is equal to 0, the starting condition, the motor produces a torque called starting torque, which is this is the torque. So for low slip region, the speed near the region is stable. So it is stable up to this torque. And once it reaches the maximum torque, the characteristics torque reduces here. So this is the the region where the torque starts reducing. So this is the starting torque, maximum starting torque Tm, and this is the full load torque. It is a full load point, stable operating point. And the for low slip region, as I said, the speed near the region is stable and the characteristics is a straight line in nature. Fall in speed from no load to full load is about 4 to 6%. The characteristics is as shown here. It can be seen from the figure that the stable region of operation, the characteristics is similar to that of DC shunt motor. So due to this, three-phase induction motor is practically said to be constant speed motor, as drop in speed from no load to full load is not significant. So the unstable region of operation is, this is the dotted line shown where it is the unstable region of the operation. Now coming to the effect of rotor resistance on the torque and slip. So effect of rotor resistance, as you see, the slip ring induction motor, external resistance can be added into the rotor circuit. Let us see the change in rotor resistance on the torque produced. If you take up, let R2 is the rotor resistance per phase corresponding to torque. So in that case, the torque equation we have, T is proportional to S, as we see here, T is proportional to S E2 square R2 into this is K, as I denoted, R2 square by X2 square. So taking at that equation, so we can explain this torque. So corresponding this similar torque at S is equal to 1, if you observe, S is equal to 1, maximum R2 and R2 dash can be written as R2 dash very related to R2 dash. So if R2 dash is greater than R2, then SM, the slip, is greater than the maximum slip. So if you observe here, torque with original R2, if R2 dash is greater than R2, then the slip starts increasing. Due to this, we get a new torque characteristics for rotor resistance, so which is parallel to the characteristics for with the same but Tm occurring at Sm dash. So the effect of change in rotor resistance on torque slip characteristics as shown in this figure. It can be seen that TST dash, here this one, for R2 dash is more than TST for R2. So again, if you carry for the next R2 value, T double dash ST is greater than this. So this torque is greater than this. But observe, the maximum torque remains same. So if now resistor is further added to get the resistance R2 dash and so on, it can be seen that Tm remains same, but the slip at which occurs increases Sm dash and so on. Similarly, starting torque also increases with increase in TST dash and so on. So if maximum torque Tm is required at start, then Sm is equal to 1. Maximum slip should be equal to 1. At start, slip is always unity. Therefore, R2 by X2 is equal to 1, which is equal to S. So R2 is equal to S2. Condition for getting TST is equal to Tm. So if you observe here. So as you increase the resistance, because of the slip increases, but the maximum torque remains same. It is represented by this. If such resistance keep permanently in the circuit, there will be larger copper losses and hence efficiency of the motor will be poor. So such added resistance is cut off gradually and finally removed from the rotor circuit in the normal running condition of the motor. This method is used in practice to achieve higher starting torque, and hence resistance in rotor is added only at the start for good performance at start, and in the running condition is ensured where the resistance is being removed. Thank you for watching this video.